Thank you everyone for coming. So today we have Amir, he will present about his PhD, but the formal introduction I will ask Alistair, that was his PhD supervisor, to do. So I will go aside. Alistair.
Thanks very much, Siv. Welcome everyone. I'll introduce Amir and his work, but I'm sure Amir's going to tell us all about it, which is great. Amir came to do his PhD, and coming from Egypt, Amir had very strong ideas about the sorts of things he wanted to do, and so I think he's done a great job. He managed to convince myself and Greg Leslie that we should get involved in this project, and Amir has been the one who has driven it right from the start. So he's done a great job. The good news too is that Amir is giving you this talk on the at the end of his PhD. So he's had it examined and he's got good results back. So he's smiling. But I'm also very glad that Amir is able to stand up here today and present to an audience such as yourselves. I'm always encouraging my PhD students to present, because it's a very good thing. No matter how good your technical work is, you've got to be able to communicate that to an audience. So I'd better get out of the way and wish Amir well. And
Thank you.
Interested to hear what he's got to say.
Thank you.
Thanks, Amir.
Okay, so today I'll be presenting the main results of my PhD thesis, which is about high recovery rate solar-driven desalination plants for brackish groundwater extraction and desalination in Egypt. So it's a seemingly complicated title, but I'll explain it as I go further with my presentation. In this presentation, I will try to answer 4 main questions. So first, why do we need decentralized plants for high recovery rate solar-driven plants for brackish groundwater extraction and desalination in Egypt? Secondly, is it more economical to use a photovoltaic system to run a PV, like a reverse osmosis plant than a diesel generator? The third question is, what if we use PVT collectors instead of PV modules? Would it be more economical? And the last question is it feasible to use a membrane distillation process to increase the recovery rate of an RO plant, like a reverse osmosis plant? So let's see. So first I want to start that I know most of you heard here about doom and gloom scenarios that other heard or talked about it. Lots of people talked about what can we do to avoid these kinds of scenarios. But in Egypt it's kind of different, because it seems that these doom and gloom scenarios are already happening. So the question now is not what can we do to prevent it, but what can we do to get out of it? And I will show that now. So I will go with a review on energy and water availability in Egypt. So and I'll talk first about fossil fuel availability. So as you can see here, Egypt is a net oil importer. And for our natural gas reserves, I estimated that if with the same growth rate, they will be exhausted by 2028. And I need to mention that Egypt, 84% of the energy supplies comes from oil and natural gas in Egypt, and the rest is from hydropower. And secondly, for example, the natural gas, we used to export it, but the recent years we start to import it. The second part is that since 2010, every summer we experience electricity shortages, electricity cutouts. Okay, and it was worse last year. In some cases, the electricity was cut out for 6 hours a day in all cities in Egypt. And this was attributed to the lack of fuel supplies for the power plants, as well as aging infrastructure. And you can see here this cartoon, which is the Arabic, was written in Arabic, and this is the natural evolution of the Egyptian citizen. So it will turn into bat, so you can see in the dark, which I find very funny. Okay, now for water, 70% of the fresh water resource comes from the Nile River. That's the main supply. And then when you account for the amount of Nile River that is reused, what I mean by reused is that most of the cultivated lands in Egypt, they are along the Nile River. So the excess irrigation water just goes back to the irrigation canals and the Nile River itself and reused. Okay, so when you account for that, you find that 96% of Egypt fresh water comes from the Nile River. Okay, and the other, we have small contribution of groundwater, wastewater, and seawater desalination. Like seawater desalination, almost negligible contribution. So let's see. We can see here from the graph here that we're almost exhausting all our Nile water, available Nile water, whether from reuse or the main Nile water. Groundwater we have limited resources, but it's highly underutilized, and seawater desalination is essentially indefinite. So, and I need to mention that, okay, what do I mean here? Well, like, will we die of thirst? No, not really, but the problem is that most of the people, okay, let me rephrase that. So farming, which was like practiced in Egypt since 6,000 years ago, will not be our thing anymore. So that's the main problem. So, and what is even worse is that the Nile River is shared among like 9 other countries, okay? And Egypt is the downstream country. So if any of the other countries decided to build dams to impound the flow, this will greatly affect Egypt. And let's give an example, a realistic example. So 85% of Nile water that reaches Egypt comes from Ethiopia, from the Blue Nile. And Ethiopia recently, if you heard, they're already constructing the Grand Renaissance Dam. That's a huge dam. It will be the biggest in Africa. And it has a huge reservoir of 74 billion cubic meter. And I estimated that from the evaporation losses alone from this great reservoir, it will result in a 4% reduction in Nile water availability in Egypt. So you can think, what 4% is not that much, but 4% it means 2.3 billion cubic meter. So you can imagine how many desalination plants we need to account for this loss. It's huge. And secondly, and most importantly, so Ethiopia government, they claim that this dam will be only used for hydroelectricity generation. But it was reported that to meet the increasing food demand, especially that Ethiopia currently rely on rainfall irrigation, which is unreliable and irregular, and that's why they have plans to use the water from the dams for irrigation. And actually, there was a proposal by the U.S. Bureau of Reclamation to build dams in Ethiopia to cultivate 400,000 hectares of land. So I estimated if they're going to irrigate these lands, even with the most water efficient technology, this will eventually result in 19% reduction in Nile water availability, and that will be huge. And again, I'm not like, I don't want to get into politics. I actually believe that Ethiopia, they have the right to use their water, but all I'm saying that will still have a great impact on Egypt. So the conclusion is that to augment Egypt's water supply, we either have groundwater extraction or seawater desalination. So I mentioned before that groundwater is limited and seawater is essentially unlimited. But the question is there any potential benefit for extracting groundwater, although it's a limited resource? So let's see. So we can see here from the map that most of Egypt's area is inland. So if you're going to build desalination plants, you'll have to build centralized, large-scale desalination plants and convey the water to inland areas. You don't have any other option. On the other hand, if you're going to extract groundwater, it gives you the chance to build small-scale decentralized systems. So the question is there any benefit of decentralization in comparison to centralization? So I'm basing here my ideas based on the book by Schumacher, Small is Beautiful, and most of you maybe know about it, and I was actually inspired by this book. So this author, he argued that centralization is unsustainable and promotes inequity, and this is exactly what's happening in Egypt. So it was reported that most of the development efforts in Egypt were concentrated in major cities such as Cairo and Alexandria. Okay, but for other cities, actually the poverty rates were increasing. And the second point, of course, when you build decentralized communities, you need small-scale infrastructure, which is easier to finance, and that's important for a poor country like Egypt. Thirdly, what Schumacher also argued is that if you build decentralized communities where the people can work in the same area and use local skills, that will increase the resiliency of the population. So what I'm particularly suggesting is to create decentralized agricultural communities with local access of water from the ground and energy from the sun. And why is that? I already showed you that the shortages in water will mainly affect the farmers, okay? And you need to know that the farmers, they constitute third of the workforce in Egypt, and they basically live in rural areas where poverty rates are the highest. Thirdly, you may know that the food and energy supplies in Egypt are heavily subsidized, but the government decided that they will gradually remove these subsidies within 5 years, and this will compromise the resiliency of the population. And also the farmers are not just losing their jobs due to lack of water, but they also due to urban encroachment. So if you can see here, that's the population map. So you can see most of the population, not most, like 90% of the population are concentrated in the Nile River. And this is where the arable land exists as well. So you either put arable lands or buildings. And what happens is you put buildings. That's what's happening now. And I need to mention, I forgot to mention one story, is that in some cases, due to the lack of fresh water, that was reported in many areas in Egypt. The farmers actually used wastewater to irrigate the land. And it actually eventually led to degradation of the land. The land was not suitable for irrigation anymore because the water was not suitable for irrigation. So this is how bad it is. And in some cases also they use the water for drinking. And you have some cities like Matruh, they actually have like thirst problem because the farmers were stealing the water meant for drinking. So you can see it is happening and it is serious. And I'm suggesting soil resource, of course, because Egypt has huge soil resources, okay, as you can see from the map. It was one of the highest in the world. Maybe some of you can ask, okay, why not wind energy, which is cheaper? But the problem is that the only location where wind energy, like the wind's velocity, are high enough for wind to be economical is just, okay, maybe it's not clear here. It's just somewhere here around the Gulf of Suez. That's it. But the rest of the land, it's not economical to use wind energy. So the question now, where can we find groundwater? And what is the quality of the groundwater? Is it suitable for drinking and irrigation? And what is the potential for sustainable development for the aquifers? So that's the third thing I did in my thesis, to investigate that in Egypt. So after reviewing groundwater, I found out the following, that 55% of Egypt is covered by brackish water, like has access to brackish water. And we have huge access to fresh water as well, which is the blue area. But as you can see, this blue area is so far from the Nile Valley and the delta, from the Nile River. Like basically they are so far from areas with access to infrastructure. So the problem now is that no one will want to move there. And this is actually happening. So there was a project called the Toshka project where they built a huge canal to transport Nile water to the desert, okay, in the western desert. And no one moved there. So what happens, like no one settled there and moved with their family. So it was not that successful. This is, for example, in comparison with another project where they did the same, but near the delta area between Cairo and Alexandria. And because it was close to the area of infrastructure, you can actually see, like in 3 years, this place becomes very populated with lots of agricultural lands and houses. So that's a huge difference. So what I concluded is that it's better to extract brackish water because it gives the chance to gradually expand out of the Nile River and Nile Valley and Delta. And what I found also that out of these brackish areas with brackish water access, 47% have moderate to high potential for sustainable extraction. And what I mean by that is that I did a multi-criteria analysis based on the productivity of the wells, the depth of the water table, because it's important because it affects the costs associated with groundwater extraction, and the renewability of the aquifers. So is it fossil water, which like will be depleted in a while, like in a few years, or it's renewable water, you can keep using it. Okay, so that's what I based my analysis on. That's the map in Sinai Peninsula. You can see also mostly it has access to brackish water and only a small part to fresh water. So now, as I'm suggesting to extract brackish water, there is a challenge here that brackish water, which has a salinity between 1,000 to 10,000 milligrams per liter, is not suitable for drinking.
Short question, brackish water and groundwater, is that the same thing or is it slightly different?
Sorry?
Is brackish water and groundwater, is it the same or is it
so I'm talking about groundwater, and groundwater has there are two options. Either it's fresh water, which has low salinity, or brackish. Brackish means it has higher salinity, which is 1,000 to 10,000. Okay, so in order for brackish water to be suitable for drinking, you definitely need desalination. Okay, so what are the challenges? Like desalination is an energy-intensive process, and of course it's a costly process. Okay, so you need to find a way to reduce the energy and the cost of such process. And secondly, with any desalination process, you have the problem of brine disposal. So what is the brine? The brine is basically the reject. Like so, usually when you desalinate water, you don't desalinate all the water. So you have the fresh water and the remainder, which is like full of salts and chemicals. And usually you have problem in disposing that due to environmental concerns. And secondly, I already noted that groundwater is a limited resource, so you better make use of every bit of it. And that's why we need a high recovery rate desalination. What I mean by recovery rate is that the amount of water you desalinate from the feed water. So for example, a recovery rate of 50% means that if the feed water is 2 meter cubic, okay, you're producing 1 meter, you're only desalinating 1 meter cube, okay? And this is why my topic was related to high recovery rate solar-driven plants for brackish groundwater extraction and desalination. So now let's go through solar-driven desalination. So basically, you have two types of desalination processes, those based on heat and those based on electricity, okay? So those based on heat, such as multi-stage flash distillation, multi-effect distillation, and so on. I will not go through explaining each one of them, but basically they all work with a similar idea, which is you heat the water, it evaporates, and then you condense the water vapor, and you get distilled water, like pure water, okay? The other parts, you have desalination processes like they use electricity. They are mainly membrane-based processes, so they use a membrane, such as reverse osmosis and electrodialysis. You have also two phase change processes like freezing and mechanical vapor compression. These are phase change processes. Now that I'm talking about solar-driven desalination, for heat-based desalination processes, you can only use flat plate collectors, evacuated tube collectors, or compound parabolic collectors, and of course solar ponds, okay? But in the context of Egypt, I focused mainly, or I concluded that flat plate collectors are suitable. Why? Because they are the cheaper option, the cheapest option. And secondly, they can supply water temperatures up to 90 degrees, which is enough to drive most of these processes, okay? So when do we use evacuated tube collectors or compound parabolic collectors? These two were specifically recommended for areas that are cold, because you expect high heat losses, and that's why you use them. But in Egypt, it's a warm country, so there's no you don't need these kind of technologies. As for solar ponds, they're only economical for large-scale applications, and you have the issue of evaporation losses. So you need to continually replenish the water. And I mentioned before that we have water problems, so that's not a very good idea. Now for the other electricity-based desalination process, you have photovoltaics, concentrated photovoltaics, and CSPs, okay? And what I concluded that photovoltaics is still the best option to run these kinds of processes. Why? Because it's still the cheapest. So this is the levelized cost of electricity of each technology. So you can see that utility scale ground-mounted PV is still the cheapest, okay? Not just that. The CSP plants, they're usually not suitable for small-scale applications, and except the one using parabolic dishes, but they are very expensive. On top of that, there was a report by the Fraunhofer Institute that predicted that the cost of CSPs will still be higher than PV even in 2030, and with the same rate as the same difference as it is in 2012. And this was attributed to the slow learning curve of such technology. However, there is a great prospect for concentrated photovoltaics, and I'll recap on that at the end of my presentation. So currently the cost is 27 cents per kilowatt hour, but many studies, they projected that the cost will drop to 6 to 8 cents in the next few years. I mean, in the next 5 years. So I believe it has great prospect. As for desalination process, desalination process itself, I conclude that reverse osmosis is the most suitable for the application that I'm discussing here, which is decentralized brackish water desalination. And why is that? Reverse osmosis in general has the lowest energy consumption amongst all other processes, and with brackish water it even becomes lower. And why is that? Because the energy consumption in the reverse osmosis process, I will explain in a while, is directly proportional to the amount of salinity in the water. On the other hand, those heat-based processes, they are not that affected with the salinity, and I will show that in a while. Secondly, they have the lowest levelized cost of water. Even for seawater, they are the cheaper. Although they have high operating costs, especially regarding maintenance, they're still the cheapest option. And this can be seen because they are most widely used. 65% of the worldwide installed capacity of desalinated water comes from a reverse osmosis plant. Fourthly, and most importantly, in Egypt, 89% of the desalination plants, they use an RO process. Okay, and besides that, there are plants that are used to assemble RO modules, and this will increase the sustainability of using such technology. And of course, modularity. Modularity means that because it comes in modules, so you can basically fit it to any scale you want, small scale, medium scale, large scale. And that's important because I'm looking for small scale applications. So that's the process description. I'll just go fast through it. So basically, the osmotic phenomena means that if you have a solution with that has low concentration of salts and a solution with a high concentration of salts, and they're separated by semi-permeable membrane. And what I mean by semi-permeable membrane is a membrane that can only allow water molecules to pass. Okay, so the osmotic phenomena means that the water from the low concentrated solution will try to cross the membrane to dilute the concentrated solution till they reach a balance. And that's why you have like the column here is higher than the column on the right side, and this difference is actually the osmotic pressure. So in order to desalinate water, you need to reverse this process. So you need to put pressure on the left side of the column so you can force the water to cross to the other side. And because the membrane has very small pores, besides other rejection mechanism, it prevents the salts from passing. So now let's discuss the techno-economic feasibility of high recovery rate PVRO plants. So what I will try to answer here, since we're looking into high recovery rate applications, what is the maximum recovery rate that can you obtain with a reverse osmosis plant? And secondly, is it more economical to use photovoltaics than diesel generators? So let's see. So that's the plant configuration. So basically you're extracting the water, it goes to the reverse osmosis plant, the permeate water is stored, and the concentrated water is rejected in deep injection wells, okay? And I did the simulation here using PVSys and ROSA, which is a commercial simulation tool for the reverse osmosis process. And I also investigated the design for two cases. The case where the PVRO plant is designed to work only during daytime. So in this case, the battery is only used for power conditioning. And the other case where the reverse osmosis plant is working for 24 hours. Here I need to stop and mention, okay, these kind of studies were done before, so what's new here? The point is, what I noticed in the literature, all the plants that I reviewed, they were working on a very low recovery rate. So some of, like, mostly below 50%. And it's not economical, especially with brackish water, specifically talking about brackish water, to work with such low recovery rates. And secondly, most of them were designed in a very ad hoc manner. So most of them were not following the manufacturer recommended operation, which means that if you actually apply this plant in real life, it will not last for more than 2 years or something. Okay, and and this was like I was sure of that because I went to Cyprus like in 2011 with the Fraunhofer team, like soil desalination team, and I found that they did the same exactly. They designed the plant in an ad hoc manner, and the RO modules were working outside the recommended window. And like I helped them to fix that data, but this is what I noticed in the literature and from actual experience. And third, usually when I find economical analysis that was done for PVRO plants, it's for a specific condition. So for example, it's like a reverse osmosis plant working with 2000 salinity and certain recovery rate. But what I want is I want to get the greater picture, which is investigate the feasibility for several operating conditions. So I can get a better picture. So when I say, okay, the cost is between this X and Y, you can know, okay, this cost belongs to this operating conditions, and you can have a picture what this cost actually represent. So first, let's see the maximum attainable recovery rate. So I need to mention here that the recovery rate in general is limited by scaling. What I mean by scaling is that water usually have ions such as calcium, sulfate, and carbonate. And at high concentration, they start to precipitate. And when they start to precipitate, they start to clog the membrane. And that's why it doesn't function well anymore. So that's your limit. When you start phase scaling, you cannot go beyond. You cannot concentrate the water beyond that. Okay? So what I did is that I investigated 3 scenarios because, of course, the value would depend on the composition of the groundwater. So I did a review on several wells and their chemical compositions. And I put 3 scenarios. One, groundwater with low scaling potential. One with typical groundwater composition in Egypt, and one with high scaling potential. As you can see, with low scaling potential, you get the highest recovery rate as expected because you don't face scaling issues as much, for example, as high scaling potential. We can see the recovery rate is much lower. But what is more interesting that the reverse osmosis plant itself has its own recovery rate limitations, which is the blue dots, which means that if you try to attain higher recovery rate, assuming there are no scaling limitation, the modules itself, they cannot support this recovery rate, and they will start to operate outside the recommended window by the manufacturer. So you have a limitation by the RO plant itself. So what I found out that for the typical groundwater composition in Egypt, you can get from 75 to 90% recovery rates, which is pretty good. So now let's discuss the economic feasibility. So of course, when I designed the system, like when I had in my mind, definitely the system that is designed to operate during daytime will be cheaper. That's my conclusion. Of course, you think about it, you need a small battery bank, so it has to be cheaper. And it is. You can see it's slightly more economical than a plant driven by diesel generator. And of course, only when the subsidies on diesel are removed. So with the current, I mentioned previously that energy and food are currently heavily subsidized by the government. So definitely with the subsidies, it's not economical to use a PV-RO plant. But what's most interesting, and I think that will interest most of you here, because this does not only apply for desalination, but any other PV applications, is that I found out when you design the plant to operate for 24 hours, although the levelized cost of electricity was higher, so in this case it was around 44 cents per kilowatt hour in comparison to 33 cents per kilowatt hour, the levelized cost of water was actually cheaper, as you can see from the graph. And why this is happening. But what I found out is that you have the RO plant, so you have the same equipment of the RO plant, but in one case you're only operating this equipment to produce water for 8 hours, and the other case you're using the same equipment and you're producing water for 24 hours, where you're getting 3 times the amount of water. And since the life cycle costs of the RO plant were much higher than that of the PV, it was cheaper to operate the plant for 24 hours, particularly for brackish water application. But because you can see here at very high salinity, let's say at 20,000, they start to get similar. Why is that? Because in this case, the energy consumption increases a lot, and now the levelized cost of the PV system start to match that of the RO plant. And then now, in this case, it doesn't really matter whether you operate for daytime or 24 hours. But for brackish water application, it's definitely better to design the plant to work for 24 hours. And I think you need to consider that, because this was not considered before. So after finding out that it's better to operate at 24 hours, I estimated the levelized cost of water for the typical groundwater composition found in Egypt and the typical groundwater depths. Okay, so it ranges between 0.7 and $1.65 per meter cube. So let's give this a context. So you can compare these are the current water prices in Egypt, like the sold to consumers. So you can see it's much cheaper than desalinating the water. But I already mentioned that it's not an option anymore to use conventional water supplies, right? So now it's better to compare with seawater PV-RO plant. So that's the competitor. So remember we asked, okay, is it better to desalinate seawater or brackish water? So we can see here the cost of desalinating seawater with the PV-RO plant is much higher from extracting and desalinating brackish water. Because the question I asked myself, okay, what about the additional cost of extracting the groundwater and construction and well construction cost? And you see there's still even with these costs, it was still cheaper to extract the water and desalinate than desalinating seawater. And you can see here that, of course, this is like the main reason for that is the huge difference in specific energy consumption. So you can see here, like the bar graph is specific energy consumption of extracting the groundwater and desalinating it. And the blue rectangle is the range of specific energy consumption of seawater desalination. So you can see it was still lower. And I forgot to mention, I'm not accounting for the extra cost and extra energy consumption that will be needed to convey the water from coastal areas to inland areas. So which means that desalinating seawater will cost much more and will consume more energy than was shown in this figure. So to recap on this part, I can only describe a PV-RO plant as a cost competitive with a diesel generator RO plant. The levelized cost of water from 7 to 16% higher than a diesel generator RO plant. So the question now, what can we do to reduce the levelized cost of water? So I did a sensitivity analysis and I found out that the interest rate and the battery cost have the highest impact on the levelized cost of water. Okay? More than anything else in the PV system costs, like the balance of system, the PV modules, and so on. So I tried to play with these variables, and I decreased the interest rate from 13 to 9%. And why 9%? Because this is basically an interest rate almost equal to the inflation rate. And definitely you cannot go beyond that. And actually, when I went to the website of the central bank, the interest rate was about 9%, which is very close to the inflation rate. Okay, but when I talked to a friend who's a banker, he told me it's better to use a more conservative value of 13%. So in this case, if the interest rate dropped to 9%, the PVRO will be only 2 to 5% more expensive than a plant driven by a diesel generator. But what is more interesting, what if the battery cost dropped from $200 to $100 per kilowatt hour? In this case, a PVRO will be definitely more economical. As you can see from the left side, like these are the different locations in Egypt. So I mean, it will be more economical for all locations in Egypt. So you can wonder, okay, is $100 per kilowatt hour something from space, like something imaginary that we can expect like in 20 years? The answer is no. This value was already used in the literature. So some authors actually use a value between $80 to $90 per kilowatt hour. Okay, I need to mention here, I'm talking about lead acid battery, okay? So this is, I believe it's already feasible. It's not something impossible. But I use $200 as a conservative value. So the question now, I said before, I'm trying to decrease the levelized cost of water of a PVRO plant. So what can we do more? So the other idea what came, okay, what if we replace the PV modules by PVT collectors? Why is that? So we have a double benefit here. So I can use the pumped groundwater to cool the panels, which will increase the annual yield of the PV cells. And not just that. With RO plants, if you heated the water, it will reduce the energy consumption of the process. Why is that? Because basically, when you increase the water temperature, you decrease the viscosity of the water. So water molecules can pass easier through the membrane. Okay? So for the same energy consumption, you're producing more permeate flow. And that's why the specific energy consumption drops. But this comes on an expense that as much as you let more water molecules to pass, you let more salts to pass as well. So this will affect the permeate quality. Okay? So I investigated, okay, the effect of water temperature on the power consumption. So you can see from this figure, up to 30% reduction in power consumption can be achieved without compromising the permeate quality. So in this case, like even in the worst case scenario, the permeate quality was around 600 milligrams per liter, which is still within the recommended range. So I can get 30% and no compromise in water quality. But there is a catch here. Because what I found that you can only get the aforementioned power savings only if the RO modules are allowed to operate outside the recommended window. And in some cases, I exceeded like the recommended window by 58%. And why is that? So when you increase the temperature and increase the permeate flow, it starts to exceed the recommended window. So to counter that, if you want to properly design the system, you will have to use high salt rejection membranes. But if you use high salt rejection membranes, okay, you limit the amount of salts that is passing. So in this case, you increase the osmotic pressure. So basically, you're countering the effect of increasing the water temperature. And that's why if I properly design the system, you can see you got no saving in specific energy consumption. So that's one catch. So I said, okay, let's walk the extra mile and assume that we can operate outside the recommended window without a major impact on the RO modules. So I designed, I just came up with this system. So as you can see, like the water, we go through the PVT collectors instead of PV modules. And I use transits to do a yearly simulation. And I use as well the model developed by Jose, who's here. It was like a more accurate model because it includes the effect of sky temperature, which gives more accurate results. So the main challenge with this design was that the RO modules, they have a maximum operating temperature, around 45 degrees. So the main challenge was to come up with a design that can protect or can prevent the RO membranes from operating beyond this value. Okay? So the idea that came to me is that I divided the collectors into two areas. Okay? So when the temperature will start to exceed this value, I will divert all the flow rate to only one section of the PVT collectors in order to limit the water temperature increase. But this has a problem, is that the other PVT collectors will work at stagnant conditions. But that's the only solution I could have come with. So let's see the results. So these are the percentage increase in the annual PV yield. And it was very small. It ranged from 3.6 to 6.7%. And these are for the different locations in Egypt. for the reduction in the RO energy requirements, it was also small, and it ranged from 3.4 to 6.6%. So remember, when I first investigated the power consumption and I heated the water to 40 degrees, I got from 12 to 30% reduction. But when I actually used PVT collectors, it dropped to 3.4 to 6.6%. And of course, before going to that, and of course, with this more reduction, when I calculated the levelized cost of water, it was actually more expensive to use PVT collectors. Okay? You can see here, like, these three cases are the best possible cases. So I said, okay, I'll take the case which has the highest percentage increase in the annual yield, the case where it has the highest reduction in the RO plant energy consumption, and the case where you have the highest net energy saving, which means that you have the summation of the amount of increase in the yield from the PV cells and the reduction from the RO plant is the highest. And even for the best cases, it's still more expensive. So why is that? Of course, when you think about it, it's the low capacity factor of the PVT collectors, because it's impossible to heat the water to 40 degrees all the time, because basically the sun only shines during the day, and even during the day, the solar radiance, it varies. So you cannot get 40 degrees, constant 40 degrees temperature. When I mean 40 degrees, it's just about like near the maximum temperature of the RO module. And that's why the value dropped from 30% to a value as low as 6.6%. Secondly, there is the operation temperature limitation to our plant. So you cannot just say, okay, I will use a huge PVT collector area to increase the temperature. You cannot do that, because you will exceed the maximum temperature of the RO modules. And in my design, it will mean that higher, a section of the PVT collectors will work on stagnant conditions for a longer time. And it will actually decrease the yield. And that's like, for example, an example here. So you can see that's the temperature of the main collectors. So in this case, the water was diverted to only to the main collectors. And you can see the left out one, the auxiliary collector, was working at temperature slightly higher than the PV module. So it was not that effective. Like, it was actually the yield from these collectors was less than the PV. The third problem is that when I accounted for the energy savings I got from PVT collectors, I found that it only resulted in a reduction in the cost of the PV module. And I mentioned before that from the sensitivity analysis, the greatest impact was from the battery cost, from the battery bank, not the PV modules. For the battery bank here, for the PVT collectors, the maximum reduction I got was 3%, which is nothing. And I want even further mine, and assumed, okay, what if even we said the PVT collectors, if we convert PV modules to PVT collectors, will cost us nothing. Even in this case, I got only 2% decrease in the levelized cost of water. So I concluded that this is not the way to go. Although potentially it seemed very, very attractive, it's not. And I can't see a way out of this. Like, I kept thinking, okay, is there something we can fix to change that? I couldn't come with any answer to that. So I don't think that's the way to go. Now, I spoke before that we need a high recovery rate operation, because we want to make most use of the groundwater, which is limited. Okay, so how can we do that? Okay, I need to mention that with the reverse osmosis plant, the ceiling of recovery rate that I can obtain was from 80 to 90%. So can we go beyond this value? The question is yes, if we use a thermal process, because I mentioned before that thermal processes are less sensitive to water salinity. Okay, and you don't have the pressure limitation or the module limitation as in RO process. So no pressure limitation. The production is less affected by water salinity. So I give an example here. If I increase the feed salinity from 35,000 milligrams per liter to 50,000, with a thermal process such as membrane distillation, you get 70% decrease in the energy consumption. But with the reverse osmosis, it's directly proportional. So you get 43% increase in the energy consumption. And I particularly suggested the use of membrane distillation to desalinate the brine of the RO plant. Why is that? Because this technology is robust and simple, so it suits standalone applications, like in remote areas, in the concept of decentralized communities, because I want it to be sustainable. Second, it's modular, similar to our reverse osmosis, so it suits small-scale applications. Thirdly, it needs a low-grade source of heat, so basically you can use simple flat plate collectors to run the process. And it also works on low pressure, like atmospheric pressure, so you don't need extra equipment. So for example, like most of the phase change desalination process, you have to work on low, like vacuum pressure, or low pressure than atmospheric pressure. And finally, it has large potential for improvement. That's the most important. So most of the membrane used now, they actually borrow membranes from other processes, such as microfiltration. I can talk about that later, but there are no dedicated membranes that are used for membrane distillation. So that's like the process. I will not go through it, but basically you evaporate the water, like use a hydrophobic membrane, which prevents the water from passing through the pores. So that's a section of the membrane. Okay, so only water vapor molecules are allowed to pass through the pores, and then you condense it from the other side. So one side there's hot water, and one side you use cool water to condense the water vapor molecules. So I need to mention, okay, the hybrid ROMD concept was investigated before in the literature, but it was only investigated for seawater applications, which I don't believe is really that important because seawater is essentially indefinite. So why would you need to increase the recovery rate with seawater applications? But most importantly, all the existing studies are based on the lab scale module performance in this study by Drioli al. But the problem is, like with lab scale modules, you can get very high flux values that cannot be achieved with full scale modules. So it gives an unrealistic results. And secondly, in these studies, they estimate a specific heat consumption of around 13 kilowatt hours per meter cube, which is not realistic. That's impossible. You cannot get specific heat consumption with a phase change process with that low. Like the lowest in the literature reported was around 50 kilowatt hours per meter cube. So I really doubt the validity of these studies. And secondly, like I will skip this part, but this one means that they also reported flux at this high salinity, which I believe it's impossible because you will face scaling issues at this high salinity. So what I found out that you need a new feasibility studies based on a full scale module. In other words, you need a new study based on more realistic data. So in my case, I used this particular kind of module, which is called the permeate gap membrane distillation module, which in this case it's a spiral wound module. And I choose this one because it's this is the only module which has experimental data in the literature, because I need to create a model for that so I can play with it and see the effect of different operating conditions on it. Now, the main problem with the modeling such module was that to account for the heat transfer between the different layers in the spiral wound module. This was not done before in the literature. Like all the existing models were based on lab scale modules, so you only got one small portion of the membrane. So you really don't have effect of multi-layers and heat transfer from multi-layers, okay? So that's what the main challenge. So what I did is that I converted this spiral wound into this shape, which is in the shape of Archimedean spirals. And like it took me a really long time like staring at this photo, and I started actually to dream about this photo. Yeah, but it actually works. I finally could take into account the different heat transfer between each layer, and that was really intense. So these are the results, and you see I got very good agreement experimental results with no more than 3.3% deviation, like mean deviation from experimental values. I will not go through that because this will need another seminar. So basically that's the configuration I'm suggesting for a hybrid RO plant. So basically you're taking the brine from the RO plant and you keep recirculating it through a solid-driven membrane distillation process till you get the recovery rate required. So now I focus like this system. So this is how the solid-driven membrane distillation will work. And I will skip that because I think I'm running out of time. And that's the transit model. Let's show it. So the first question, okay, now that we use the membrane distillation, what is the maximum recovery rate that we can achieve? First, as I mentioned before, you have scaling limitation. So even with membrane distillation process, you will have exactly the same limitation. So in this case, the only way you can get higher recovery rate than that obtained from an RO plant, which is the blue dots, is for groundwater to have a low scaling potential, because else you cannot concentrate it to these high values, okay? So the only way, and of course, a low scaling potential groundwater is like, it's not the typical groundwater that you can find in Egypt or anywhere else in the world. So definitely, if you're going to use a membrane distillation process, you need additional pretreatment requirements. So there are things like using media filters and lime softening and stuff like that to remove all the ions that cause scaling, and then you can concentrate it to higher values. And this was shown, and it's actually possible, like this study by Martinetti, it shows that with this kind of additional pretreatment, you can reach up to 98% recovery rate. So I went, okay, let's say we use this additional pretreatment. And I was expecting, let's go back, that I will definitely get a recovery rate higher than the red dots, because now I don't have any scaling limitations, right? So I expect, okay, definitely I'll get high recovery. So when I ran the Transys model, I found that the recovery rates were actually lower. I was, what? This doesn't make sense. What I found out is that, so actually no more than 10% enhancement in the recovery rate was obtained, although I assumed that the water can be desalinated to this concentration, like 250 grams per kilogram, without experiencing any scaling. So when I investigated the issue, I found that, okay, I should have explained this before, sorry. So in this configuration, you need a cooling tower because you're using the water from the brine as the coolant, okay? So each time you circulate it through the membrane distillation, it got warmer. So in order to reuse it again, you need to cool it, okay? So that's why else the temperature will keep increasing and the process will stop. So you need the cooling, definitely need the cooling tower. So let's go back. So what I found is that this cooling tower has 2.2%, like as minimum as 2.2% evaporation losses. And you can think, oh, this is small. But the problem with this was the main recovery rate limiting effect. And why is that? Because the water goes through the membrane distillation process, part of it evaporates, so it gets more concentrated. But in the meantime, the brine goes through the cooling tower and evaporates, and part of it gets concentrated. So what happens that you can see the difference between like the purple line and the red line. You get the water like reaches like get closer to the maximum salinity much faster. Okay, do you understand? Do you understand this part? So that's the main problem. Okay, and that's why I reached the scaling limitation very fast. Although the membrane distillation module did not produce as much as water, and that's why the recovery rate was much lower. Oh, and this was mainly because this membrane distillation module that I used had a very low recovery rate. What I mean by low recovery rate, it means that you need to circulate a huge amount of brine. So if circulating, let's say, like I don't know, like like a higher amount of brine, it means that the amount of it means that you have higher evaporation losses because you need to circulate more water. Okay. So the question now, maybe I used the wrong module. What if we use another enhanced configuration that has high recovery rate? Will it improve the situation? So I focus on this module. It's called the MEMSIS module. This kind of module uses a vapor-based membrane distillation process. So basically, they use a vacuum on the cooling side, which enhances the production. And this one has 9 times the recovery rate of this module. And when I investigated the maximum recovery rate, I found it was still lower. How come? What I found out is this module, although it has higher recovery rate, but it uses a separate channel for the coolant, and the coolant flow rate that is required is 9 times the feed flow rate. And this coolant water, again, it has to go through the cooling tower, right? So we still have the same problem. And that's why I got similar recovery rate. That's basically what I'm saying here. So I went further. I went like the extra mile. So I mentioned before that no more than 10% enhancement in the recovery rate is possible with an ROMD plant. Okay? So even with this more enhancement, is it economically feasible? So let's see. This is the MD plant performance. I was intending to explain it, but I don't have time. So that's like a typical summer day and explains how the optimization was done. So I basically optimized the plant to minimize the cost. And this like has to play with lots of variables, but yeah, unfortunately there's no time to go through that. So what I found that the realized cost of water was so expensive. It was like up to 3.69 times higher than that of an RO plant. So you got like no more than 10% recovery rate, and you got 3.6 folds increase in the realized cost of water. Why so expensive? So I did a cost breakdown for the MD plant, and I found that the highest costs come from the flat plate collectors as well as the MD modules. Of course, here you have the 22%, which has come from the indirect cost, which is basically a function of the direct cost. Like I assumed it's like 30% of direct cost. Okay? So I concluded that the main issue is that this particular module that I use, it has a very low flux, which increased the number of modules required, and a very high specific heat consumption. And that's why you need a huge flat plate collector area. So what can we do to decrease the levelized cost of water? Is there what can we change? We do. So I investigated several scenarios. Okay, what if we increase the flux of the modules? What if we decrease the energy consumption? What if we decrease the cost of the module? And I found out that using a hybrid ROMD plant can become economical under these conditions. First, you need to run the plant by source of waste heat. But since I'm talking about solar energy, I'm suggesting the use of either a CPV or a CSP plant, because these have huge waste of heat. And it will be really interesting to use that to drive a desalination process. Secondly, the module needs, the energy consumption of the module needs at least to drop by 4 times, or you decrease it by 2 times and increase the flux by 2 times. And why is this varies? I'm basically saying you need to drop the specific heat consumptions by 4 times. In this case, it will be more economic. And thirdly, the module cost need to drop to this specific cost value. This value is similar to RO module. The current cost of the MD module is $360 per meter square, which is very high. So in this case, the increase in the levelized cost of water above that of the NRO plant was from 26 to 47%. And this is not that big, because you have to consider now you're desalinating water with much higher salinity, and you're increasing the recovery rate. But I still have this question. Is it worth it in general to use a thermal process to increase the recovery rate of RO plant? So I already showed that between 75 to 90% recovery rates can be achieved with a reverse osmosis plant, which is pretty good. Secondly, you need additional pre-treatment requirements to achieve high recovery rates, which will increase the cost. Thirdly, I believe the same limitations with membrane distillation process apply for all other thermal processes, because all of them, they have the same problem with needing large cooling requirements and having a low recovery rate. So the only case where this might be interesting to consider is, as some studies did, is they consider, okay, if we use, they used another technology where they actually fully concentrated the brine, so only the salt was left, and they said, okay, what if we sell this salt? And they were showing that you can actually, it can be economical if you sold the salt. But of course, I mentioned before that they were based on unrealistic results. So probably you need to redo that, considering, redo the studies with the full-scale modules and reconsider that. So to conclude, these are the 4 questions that I mentioned before. So the first question, why do we need decentralized high recovery rate solar-driven plants for brackish groundwater extraction and desalination? And the answer is that my vision is to create decentralized agriculture communities with safe access to water and energy to increase the resiliency of at least 1/3 of the workforce in Egypt. Second, I asked, okay, is it more economical to use the PV instead of DG generator to drive the RO process? And the answer is, with the current cost I use, it can be described as cost competitive, but if the battery cost dropped to $100 per kilowatt hour, it will be clearly more economical. And of course, I showed that the levelized cost of water of extracting and desalinating brackish water is actually lower than desalinating seawater. Third, is there any economic advantage of using PVT collectors instead of PV modules? And I clearly showed that no, because of the low capacity factor of PVT collectors and the variability of soil irradiance, as well as the limitation, the temperature limitation of the RO modules, it's not worth following. Finally, is it feasible to use a membrane distillation process to enhance the recovery rate of our RO plant? So I found out that you can obtain less than 10% increase in the recovery rate of the RO plant, and the evaporation loss was the main recovery rate limiting factor. And third, that if you want to go for high recovery rates, you need a new module that has high flux, like high recovery rate, and low cooling requirements. And lastly, if you want it to be more economical, you need a source of waste heat to run the membrane distillation process, and you need at least a reduction of 4 times in specific heat consumption, as well as a reduction in the cost. So future work, what I really find is interesting and really important is investigating the use of CPV plant to run a desalination plant. It doesn't have to be membrane distillation, but I think this is the way to go, because I believe so much in this technology, the concentrated PV. And if you use the extra heat to run the desalination plant, I believe that will be like it would be really economical at that. So I think that's a really interesting topic. The other topic is that lots of people were looking in using battery-less systems to run a reverse osmosis plant. But after that, I showed that if you design the system to operate for shorter hours, it's not that economical. So I guess these studies, they need to consider this factor before going and say, okay, we want to create a battery-less system. And lastly, in my case, I said that I modeled the permeate gap module, which was spiral wound, and I considered the actual geometry. But after that, I found out recently from my reviewer, who actually did a thesis on modeling this module. He actually assumed that this module was unwound, and he modeled it this way. So it will be interesting to compare the results. So does his assumption work well as well? So that for me, I think it will be interesting. Yep, and that's it. Thank you. Questions?
Really very interesting. Thanks very much. Are there opportunities for using waste heat from diesels?
From diesels? Definitely there is, but I just mentioned because I just maybe looked at a more idealistic view, because I mentioned that with diesel we have shortages in water supplies. I'm talking about the context of Egypt, and so you have a shortage of water supplies, and you have an unreliable supply of diesel. So I found like it will compromise the resiliency of the population. But definitely, using waste heat from these generators can actually be more cheaper for a while. But of course, like in the long term, it's not a good long-term solution.
I noticed you've obviously done a lot of work on this. I was wondering if having, so instead of a lead acid battery, which has a lower maximum depth of discharge and so on, what if you used other types of battery technologies that had a larger depth of discharge and therefore would be more economical, even if the battery cost?
That would be interesting, but like at this point I chose battery like lead acid because it's much cheaper. But I believe that no one considered the effect of this depth of discharge, especially with new technologies that are coming cheaper like lithium ion. So I think that would be very interesting. But I believe for now, in the context in Egypt or any developing country, using lead acid batteries is better because they are available and we can actually manufacture it. Instead of like we have to import lithium ion, I don't think we can manufacture lithium ion batteries because they are more complicated. And that's why in the context of a sustainable solution in decentralized areas, remote areas, I preferred using lead acid batteries. But what you say is definitely interesting. Yep, because for my design, for example, I had to work with a maximum depth of discharge of 20%. So like maximum annual average daily depth of discharge of 20%, which would put further limitations on the battery bank.
In countries where the solar variability is quite high, like modern countries like Germany, people start thinking about using power to gas. And power to gas is a process where there's a lot of waste heat produced, and no one quite knows what to do with it at the moment. So I wonder if at some point power to gas might be used in countries like Egypt as well. It might be interesting to combine these two.
Sorry, can you repeat again? To use gas?
Power to gas, it's a technology to extract carbon dioxide from the atmosphere
okay.
and produce methane gas using PV electricity.
That would be definitely interesting. Yeah.
And it has, like, the process has a lot of waste heat.
That would be also interesting. That would be definitely interesting. Yep. But like I wonder now, I still believe on the short term, using something like CPV would still be cheaper, because I think this technology is still expensive. As far as I know, I don't know very much. Like I'm asking you, it's still like in early commercialization. Yep. Trent, ask first.
I was just going to follow sort of question statement on what Nitin was saying. There's a technology called aqueous ion batteries.
Pardon?
There's a technology called aqueous hybrid ion batteries, AHI batteries, that have been recently developed on the East Coast of the United States. And I mean, your comment about them being, about technologies being developed.
Yep.
You know, you don't want to develop a new technology in your country. Well, the new technology is being developed in the United States now, and it doesn't necessarily require materials that are less accessible than lead acid batteries to Egypt.
Yep.
For example, they're deliberately designed to be non-toxic and probably not terribly fancy. And the word is they're working better than lithium ion or lead acid, and cheaper. So I wonder if you've considered such technologies.
Again,
I don't know if there are many out there.
Definitely there are like better technology, but I told you again, my point then is that it was the cheapest option to use lead acid battery, but most importantly, they can be manufactured in Egypt. Like this kind of high technology, we don't have this technology in Egypt, so it exists in America. So what happens is that you will have to import such batteries from America or from any other countries, which I believe will compromise the sustainability. You want something that is locally available. That's what is very important in my study. But definitely, if it becomes locally available and it's cheaper, yeah, definitely, why not we use it? But definitely, I want to minimize the need to import some stuff. Some stuff we cannot manufacture. That's the most important.
My point is that they're cheaper. They're as cheap as lead acid batteries, and they're being imported from wherever they're used, in America or not.
I need to investigate.
So I don't see that. I don't see your point there really. I guess.
Yeah, first, like I don't know about this type of battery, but yeah, if it's cheaper, then definitely it will be a better solution. Yep.
Probably I missed your point a little bit on why you haven't further investigated only thermal distillation.
Only thermal distillation?
Yeah, that you just have huge heat exchangers heating up with the sun and distilling stuff. Because,
as I mentioned before, like reverse osmosis is the cheapest option. So that's your base. Because it's the cheapest. Basically, that's it. That's why it's better to most of the recovery rate to be obtained from a reverse osmosis plant because it's cheaper. I'll give you an example. The specific electricity consumption of the reverse osmosis alone, okay, is less than just the extra electricity needed in a thermal process plant just to circulate the water. Basically, like even without considering the heat. So it's like in I believe other technologies that are not even competitive with RO. And I showed that 65% of the installed capacity use reverse osmosis plant. So definitely now it's a super technology now that exists. But it's an interesting point. Yep.
I'll keep it brief, but yeah, great research and appreciate how thorough you've been and everything. One of the take-home things for me was just what you said about operating, because obviously when the sun's shining you'd operate then, but obviously one of the things that came out of the research is just because of how expensive those desalination plants are, it kind of overweighs any technology changes in the energy production. Where are we on the cost curve in terms of desalination? Are they getting cheaper? Are desalination plants getting cheaper? Is that?
I'm not sure about that, but I believe they're kind of reaching a plateau because it's not like a new technology or people are researching. Yeah, there are some research for like better quality RO membranes, but like it's kind of a very well-established technology. So it's kind of, yeah, not all people are researching on it. So most of the development effort are trying to decrease the energy consumption of the RO plant. So that's what I know about. But I don't believe there is a huge decrease in the application. It's like it's different than PV, for example. And that's why, that's my answer. Yeah, but definitely there has to be a decrease in the cost. Yeah.
Let's thank Amir again for great talk.
Okay.